And welcome, Mindsetters, to this session of Learn Extra, looking at grade 11 science. I hope you guys are ready. You got your pens and pads out. I am Ty, and I'm here with Tracy, who's going to be taking the lesson today. So, what's happening
Hello,
today?
Ty.
How are
It's a
you?
long time no see, hey? Anyway.
Such a long time.
It has been, 10 seconds? Anyway, so, guys, today we're looking at sound. Last week we did sound. You were here when I did it with the grade 10s. We did the same sort of thing with them with the grade 11s last week. So it's actually very cool. We played some instruments. We had some fun. It was with Kadlejo. But today what we're going to do, guys, is we're going to look at calculations. It's applications of sound, which means we've got to look at some calculations, some sort of long questions, but mainly we're looking at calculations.
All right, awesome.
Okay.
Okay, so while Tracy makes her way across the board, I'm going to tell you, Mindsetters, make sure that you get on the page and get chatting to me. Let me know what you're thinking. If you're lost anywhere, if you need help, or if you just have some really cool diagrams or anything really cool you'd like to share, feel free to let us know. Just simply post us on the page. You know the page, www.facebook.com/learn extra. So, guys, this is where I now hand over to Tracy, who's going to continue the show. Take it away, Tracy.
Excellent. Thank you, Ty.
No problem.
Well, grade 11s, I've taken a leaf out of Phil's book, actually, for you guys. He always has the challenge question. So I have a question for you guys in terms of application of sound. It is going to get posted on the Facebook page a little bit later. We are making a plan. But here's the question. Okay, so I'm going to read it to you. X and Y are different wave motions in air. X travels much faster than Y, but has a much shorter wavelength. What types of wave motion could X and Y be? Now, the way it's set out is A says to me that X is microwaves and Y is red light. X is radio waves and Y is infrared. Or X is red light and Y is sound. Or X is sound and Y is ultraviolet. Okay, so this is your challenge. Okay, so through this show, have a look at it. We'll discuss it right at the end. I'm sure some of you have got some ideas as to what the answer could possibly be. There's a little bit of a trick in this one, so think about it. Let's see how it goes. Okay? Which means, and I have chosen multiple choice for a few of these questions, grade 11s, because I think part of the problem, if I'm thinking about my own learners and what I've seen over the years, is you really struggle with multiple choice, because it's obviously one of those things that we don't do a lot of, and you sort of think it's like what we call a monkey puzzle, okay, or you play multiple guess, and you go, that sounds like a good one, which, if you know Harry, is not a bad idea, but please, 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 easiest 2 marks on your paper possible. So, first one, what is the approximate range of audible frequencies for a healthy human? Okay, we're making sure that you realize it's for a normal human, okay, not for your teachers who have supersonic hearing, we know this, okay, or for example, your great-grandparents, who we also know by the time they get to 100 really struggle to hear, their audible range has changed, okay, that's an age thing, okay, or your parents who you think cannot hear anything, okay, or sometimes you just think completely have supersonic hearing as well because they're forever telling you to turn the stereo down. Or no, you don't use stereos anymore at their age. Hey, do they even know what a stereo is? They turn the music down. Better word. I feel old.
It's usually headphones.
Yeah. We've grown out of that sharing music with everyone phase, hey?
Yeah, it's
Teenagers
kind of
don't
like
do that
music is
anymore.
my kind of situation, so I'm going to put my earphones in and disappear out of this conversation.
That's true. I forget. You know, I said to myself, I'll never be one of those people. I'm not even a parent yet. Who goes, back in my day, you know, when I went to school through the snow, which it might have been the case today. Anyway, moving on. So you've had a chance to look at the questions while I've been playing silly person. And we go, okay, let's look at the ranges. They all got 2s in front of them, so not going to help. So let's start with the bottom ends. And we go, okay. Bottom end, hopefully you all know, we can hear only to about 20 hertz. So we look at this and we go, well, that's 0.2, that's 2, there we go. Well, that means 20 hertz is an option, and nothing else has got 20 hertz, so we're hoping the other side of this is right. And it is actually, because it's 20 to 20,000 hertz. That's the frequencies we can hear. Frequencies of 20,000 hertz are those soprano sounds, those really, really high-pitched sounds. 20 hertz, those low bass notes, okay? And my voice at the moment is somewhere in the 10,000 hertz range, I think. Anyway, now this question I particularly like. Okay, it's one of my pet peeves about, well, no, actually, I love sci-fi movies, but if they actually took this into consideration, they'd be very boring. Astronauts are in a spaceship orbiting the moon. They see an explosion on the surface of the moon. And who knows, maybe the Transformers have come, the
Yes,
Decepticons
Optimus
have.
Prime has decided to.
There we go. The
to
Decepticons have
rock up.
arrived. Yes, there we go. So, why can they not hear the explosion? Well, one, they're not in the movie, okay? Options. Number 1, explosions do not occur in space. Well, certainly not option A, because if explosions couldn't occur in space, we'd have no sun. We'd have no stars. So, explosions most definitely can occur in space. Take that off. Also, humans know from experience absolutely that explosions can happen in space, okay, because we lose astronauts, we lose spaceships. It happens, okay, unfortunately. B, sound cannot travel through a vacuum. We like that option because sound is a mechanical wave, needs a medium. So that's an option. Let's just check everything else just in case. Number 1, well, C says sound is reflected away from the spaceship. Well, that doesn't make any sense because what's it reflected off? Okay, so it can't be that one. And D, sound travels too quickly in space to affect the eardrum. Well, that's a load of nonsense. So let's put that out. Oh, look at that. It was our first option. It's D. Sound cannot travel through a vacuum. Okay, so remember with sci-fi movies where you can hear the lasers and the explosions. Well, actually you can't, but the movies would be rather quiet and boring if they didn't put those noises in. Okay.
And it wouldn't be much fun if you just had the actors going bang, 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 bang.
Well, you wouldn't even hear the bang, bang.
yeah,
It'd just be-
yeah.
No, it just loses its oomph. Okay, and right now my kids are busy rolling on the floor. Because, this is what happens in my classroom. But don't tell anyone. And I'm hoping my boss isn't watching. Shh. Anyway, number 1. Next one. A sound wave is different, not the same, from a light wave, in that a sound wave is, number 1, produced by a vibrating object and a light wave is not. That is not true. Okay? Light is produced in the sun, most obvious place to get right back to the basics. Inside the sun, we have an explosion happening. That explosion causes charged particles to vibrate. That vibration of the charged particles is what gives us light. So sound and light comes from vibrating objects. Sound is not capable of traveling through a vacuum. Yep, that's true. Next one, is not capable of diffracting, and a light wave is. That's not true. All waves are capable of diffracting. Okay, earlier this year, well, no, you haven't done it yet. Sorry, the grade 10s have done it. You'll do it next year. Light is actually considered both a wave and a particle. One of the things that tells us that it's a wave is the fact that it can diffract. Sound is a wave, definitely, so sound can diffract. Nope, not C. D, it's capable of existing with a variety of frequencies, and light wave has a single frequency. Absolute nonsense. Okay? Light wave, visible light, comes in at least 7 colors: red, orange, yellow, green, blue, indigo, and violet, the colors of the rainbow. Each of those colors are characterized by a different frequency, so it's not D. So the answer there is B. Okay? Now, grade 11s, I'm hoping you're getting the hint that I'm not just stopping at the first option I think is right. I'm going through all of them to make sure I fully understand the question. Let's do the next one. At the same temperature. Hopefully you realize that it needs to be at the same temperature because there's several things that affect the speed of sound. Temperature and the medium, the density of the medium and what phase it's in. Sound waves have the fastest speed in. And now we've got the options of rock, milk, oxygen, or sand. So we go, all right, first of all, sound travels slowest in a gas. So can't be oxygen. The next slowest is a liquid. Milk is a liquid. Frozen milk, that's not what we're looking at. So we now need to make a decision. Here we're getting to now we've got a 50-50 chance, okay, of getting this right. Either it's going to go in a rock or it's going to go fastest in sand. Now we've got to think to ourselves, okay, they're both solid, so it's going to be quite fast in the solid because we realize that it's fastest in a solid. But Within that solid, the density is what now counts. Think about the fact that with sand, we have a whole bunch of little sand particles all over the place. So as sound travels through sand, it's going to travel through each of the sound particles, but then it's got to jump over a little gas particle when there's space, okay? So there's that gas particle in the middle. A rock is a solid object, okay? It's just filled with the same type of particles the whole way, no jumping over little objects, which means rocks have a greater density, okay? So if rocks have a greater density, that means sound will travel fastest in a rock. So here it wasn't quite as easy as the last three we've done, because now we had an option. So now we had to think through what we know about sound traveling through objects. Okay, now, this was not the case today because we're not having thunderstorms, okay? Here, I'm hoping some of you have at some stage gone, watched lightning because you're interested, and counted how long it takes for you to hear the thunder, okay? And you realize that when you hear thunder and lightning, when you can't hear lightning, when you see lightning and you hear the thunder almost at the same time, besides getting a huge fright, okay, you realize the storm's really, really close. Remember, light travels faster than sound. Light travels at 3 times 10 to the 8, which is what's in the question. A lightning storm creates both lightning and thunder. You can see the lightning almost immediately because light travels at 3 times 10 to the 8 meters per second, which is 300 kilometers per second. That's fast, okay? After seeing the lightning, you count 5 seconds, and then you hear the thunder. Calculate the distance to the location of the storm, really to where the lightning was, okay? It's a good way it's also a good way to decide whether a storm's getting closer or further away from you, especially if you're worried about lightning, okay? So we go, okay, I am missing a piece of information here, grade 11s, and I hope you guys are all screaming at the TV, go, there's a problem, Tracy. And if I had to pick on one of you, I'm hoping you're screaming, me, and you're saying to me, I don't know the speed of sound. Of course you don't, because I didn't give it to you. Why is it important that I give it to you? Because the speed of sound is not constant, okay? It changes depending on temperature and density. I'm going to say to you, for this problem, let's make the speed of sound 340 meters per second. 340 meters per second. I'm hoping some of you are in your heads going, no, actually, I heard once that for every 3 seconds, the storm's a kilometer away. Okay? So if it's 5 seconds, that's 1,66. So it's about 1,66 kilometers away. Let's see how right you are, because that's the theory, is that for every 3 seconds, it's a kilometer away. Okay, so we know velocity, time, 5 seconds, okay? So, velocity is distance divided by time. Don't forget that equation, grade 11s, okay? Not on the information sheet. You've been doing this equation since grade 10. And hopefully some of you even did it in grade 9 or 8. So you've been doing this equation for a long, long time. Be careful. So, be careful as well that you don't use d over t, not accepted. We have v, which is 340. We want delta x, and time is 5. So delta x is 5 times 340. Some of you are... This is where we could play fastest fingers first, you know, almost like a game show. We could turn this into a game show. And look at this. 1,700 meters. Remember, before we started this, I said it would be about 1,660 meters. That's pretty darn close, actually. Okay? And that's because of the value I used for the speed of sound. So it's actually a good way for you to predict with a storm. Next time you're in one, run away from the lightning, grade 11s, it's bad for you, okay, is for every 3 seconds, it takes for you, difference between seeing the lightning and hearing thunder, the storm is 1 kilometer away. So it's also a nice way to tell if it's getting closer to you or further apart. Okay, I'm hoping that made sense, and I'm just thinking about time, because I have lots of questions. I could do this all day. Found lots of fun ones.
We have
So,
a couple of questions. Maybe
yes.
linking to the break, we could cover this question just a little, because the thing is, I'm seeing a couple of people who've posted this. And I think like they just want more clarity in
Cool.
terms of why doesn't sound travel through a vacuum?
Brilliant. Can I answer that now? Let's
Yes.
quickly. Brilliant question. Remember, sound is a mechanical wave. When we talk about sound, the reason why you can hear me at the moment is I talk, my vocal cords vibrate. Okay, that vibration goes into the microphone, that does a whole bunch of electronic things, and then it comes eventually gets to your TV. At your TV, it goes through the TV system, gets to the speakers. The speakers of the TV, even though you can't see it, actually vibrate. That vibration causes the air molecules to vibrate, and as the air molecules move backwards and forwards as they're vibrating, they pass on their energy from one to the next. And then eventually it gets to your ears, your eardrums vibrate, etc. In space, there are no air particles. Okay? There is stuff in space, but pretty much it's a vacuum, so there's no air particles. So when I talk, my vocal cords are vibrating, but if I'm in space and there's no air around me, besides the fact I'd be dead, okay, but I'm talking, there's nothing for this energy to get transferred to. So when, like the question with the explosion, when the explosion happens, there's that sound energy, but there's nothing for it to be transferred to, which then would allow it to move on to something else. So sound has to have a medium. Light doesn't, because of the way it's created in the first place.
Okay.
I hope that helped them.
I think that helped them quite a bit.
Cool.
So, I think on that note, we can go for a little bit of an ad break. So, mindsetters, as I say all the time, make sure you tell a friend, tell another friend to get on the page and chat to us. And again, mindsetters, I cannot stress how much this is for you. And on that note, as in Tracy, you actually had a good point there in terms of the whole fastest button wins. Yes, I'm looking for the best posts, guys. If you have images, ideas, quotes, anything that's great and could contribute to the lesson, make sure you post it, because you could win these awesome prizes, this Casio calculator and this labeler. So make sure you get on the page. And I just send a quick thank you to Liberty again. But on that note, do not disappear. We'll see you after this break. And welcome back, Mindsetters. I hope you had a nice little break. And unlike me, who was being harassed about my pants. But anyway.
Can come out wrong on many times.
Anyway, on that point, Mindsetters, make sure you get on the page, chat to us, post up your questions, anything you're having issues with, or if you lost anywhere, make sure you post. And yes, I'm looking for the best post to win this awesome calculator and this labeler. So make sure you guys keep posting. But on that note, this is where I hand over to Tracy. Tracy, take it away.
Brilliant. Thanks, Ty.
Pleasure.
I know I'm going really fast, grade 11s. I'm sorry, we just have so much to go through. Actually, Ty, you made a couple of comments before the break. There were a couple there was those two comments you made, which I think we'd like to, the one about the diffraction and the one with the whales? Yes.
Okay, so basically, Sophia wanted to find out, she's a regular by the way. Hello, Sophia, just saying what up, how you doing? Anyway, she wanted to find out, what is diffraction?
Okay, sweetie, you're going to do it in grade 12. Good question. Diffraction is the bending. In grade 12, we do it with light. It's the bending of a wave through an opening. Okay? So hopefully, in grade 10, when you looked at water waves and you had a little ripple tank, and you can do this actually in the bath if you wanted to, you create little waves and you put a blockage by it and you leave a little opening. And as the waves go through that opening, they change and they bend shape. Okay, so diffraction is really just the bending of waves round a bend, basically, round a barrier. Yeah.
Okay. And then she also wanted to find out, I'm assuming this was a question because she didn't quite leave a question mark at the end of it.
Oh, it's okay.
But anyway, whales in the ocean sing to each other. The sound of their song can travel a distance of up to 800 kilometers. I've heard also elephants can do that. How is that possible?
If it's anything like elephants, I mean, I don't know what frequency their sound's made up. We have actually got a question about the sound elephants make a little bit later on.
Awesome.
Yeah, elephants make what we call an infrasound, which is a very, very low sound, which we can't actually hear. I think we can hear the whale song, but what happens is it's a very long wave, okay? So it's got a very long wavelength, which also means the energy is such that it doesn't get absorbed really easily by the things around it. Think about because you don't go to clubs. We don't do that. You go to a concert, okay?
Yes.
Because we don't go to clubs. They're all too young, and you're a good boy.
Yes.
And I'm too old. Okay, so you go to a concert, and in the concert, you hear all the noises, and you hear the sounds, and it's a great sound. Then you go outside, because now you're hungry, and you're tired, and you need to go to the toilet, or whatever, and you're standing outside the concert hall. Think about the sounds you can hear. You can hear the bass, and you can hear the drums. Sometimes you can hear those high notes, but not often because of the way it's set up, particularly in things like school halls. You hear it all the time. But those bass notes, those really deep notes, those are your low frequency notes. So those are the ones with your long wavelengths. They're the ones you can still hear. It's the same concept. Because of the length of their waves, they don't actually get absorbed by the walls and the people and all of that sort of stuff. So they're able to travel further because they don't get absorbed. It's the same concept we use when we transmit radio, in that we use long wavelengths because we want them to go further, because we don't want them to be absorbed by the trees and the hills and
everything
else.
the clouds. And
Same as it's the same concept as when you're trying to get cell phone reception.
Exactly.
Okay, trying to get cell phone reception, you're in the middle of the city and you're just surrounded by buildings. And you're like,
very likely not hear anyone.
really, really? Why? Because the cell phone towers can't pick up the frequency. So it's the same concept. With whales, I'd imagine, I don't know what frequency sound they send off. It would be an interesting thing to actually maybe find out. Is that because of the sound frequency that they send out, that sound doesn't get absorbed by the ocean, doesn't get absorbed by the water, which is a good thing, because if you think about how spread out whales are, it's a good way for them to communicate with each other over long distances. But I'd imagine it's quite low. I'm just talking off the top of my head right now. Because it can travel so far, and we can still pick it up but not with. I don't think we can actually pick it up with the naked eye. I think we have to use special.
More sonic, isn't it?
Yeah, I'm just not sure if it's subsonic or supersonic. So I'm not sure which end of the spectrum it is. Whether it's above, I'd imagine it's still below our hearing. I'm just not sure. But I'm hoping, Sweet Pea, that actually answered all your questions that we had. Okay, so I'm going to go on to some more questions about sound. And actually, this is what we were talking about with Mom and Dad telling you to put the sound down. Okay, a person is yelling. Well, we're not quite at that one, but we're getting there. A person is yelling from a second-story window to another person standing at the garden gate, 50 meters away. Now, this happens at school all the time, and it drives me mad. Okay, if the speed of sound is 344 meters per second, how long does it take the sound to reach the person standing at the gate? So, what do we know? Let's see. We know that the person is 50 meters away. Sound travels at 344 meters per second. 344. And the person is 50 meters away. So V equals delta X over delta T. We want time. V is 344. X is 50. Okay. And so delta T, the 344 goes to the bottom. Okay. And I have actually worked this out beforehand. 0.15 seconds. Okay. So you don't even notice that. Have you managed to find out what frequency it is?
Yes, we found out that frequency of whales actually ranges between 10 hertz to 31 kilohertz.
Okay, so let's just, actually I've got blank ones. Let me just write this. I'm fascinated by this.
I'm also pretty fascinated. I
this
love
is
sound
really
as
cool.
a musician, so this is
No,
awesome
but this is very cool. So it goes from 10 hertz
to about 31 kilohertz.
31
ranging.
kilohertz. Now, 31 kilohertz means that's 31,000 hertz. Okay? We can't pick up the 10 hertz. So the sound that's traveling for 800 kilometers would be in this range. Would be that very low one. Yeah, it's called infrasound.
Much like elephants.
Yeah, infrasound. Just like elephants. Elephants can make sound that you can't hear, that's of that pitch as well. And it means it travels for longer. So in water, that's actually quite interesting. It will travel very quickly in water. So that's also a big bonus for sound, because it travels much faster. 31,000, that's what you would hear. You could pick that up.
We hear the squeaky part of it.
You could hear the squeaky part,
Yeah, but you won't hear it from far. That's why you can only actually quote it from up close.
Yeah, you wouldn't. In water, they can probably hear it a little bit further because of how much faster it travels. But it's harder for us as humans to pick it up in water, though, if we're in the water. Because we're not designed to hear in water. So the 10 hertz is the one that you're hearing. And I'd imagine they only know that through special equipment. They would have put equipment in the water to
that can actually pick up
I found
sonics.
That was brilliant. I found that very fascinating. I learned something new today. Well done, Sweet Pea. That was brilliant.
That was fun.
I like that. So that brings us to this question. Okay. A piece of equipment has a warning label on it that says, "Caution, this instrument produces 140 decibels. What safety precaution should you take before turning on the instrument?" 140 decibels can burst your eardrums.
Very easily.
Very easy. Permanent damage, okay? Here you're talking, the sort of thing they're talking about here would be at airports and airplanes.
Yes, that as the engine actually cuts through the...
Yeah, no, it's ridiculous. So, thinking about what you see with those funny men who do,
they always have those muffin
shouldn't do that. I went to gym, it hurts. Okay, who do the whole semi-full thingy. Okay. What do they have on?
Those muffs?
Headphones. Yeah, they have earmuffs. Okay. So before you even think about turning this on, you put on earphones. This could also be something like a road jack. You know those jacks where they dig up the roads and before they actually make it nice and neat and all the rest of those jacks? Though we don't see a lot in this country, those things, this sort of decibels. Burst your eardrums. Okay. Very, very painful. And we were talking about earlier about turning things down. This was my mother's biggest thing when I lived at home. Turn the TV down. Promise you my mother could hear a pin drop. And I was like, what? I can't hear it. I think I was deaf, but that's okay. Now it's about your earphones. And guys, as much as your parents moan at you, and I moan at my kids all the time as well, seriously, be careful about how loud you listen to your music. Because remember, your ears are very, very delicate. And the thing with earphones is that it's very, very concentrated. I'm really glad that we're going back to the big earphones again. Those little in-ear ones, which are cool for gym, are actually really, really bad because they're even closer to the eardrums. They're not great, but the ones that surround your ears, besides getting better sound, as a musician, you should know that.
No, definitely.
It is better. But the louder you make it, and I'm sure some of you have done this, but pushed through the pain. Like you put it up in that bass, especially with house music and that sort of stuff, where it's like big bass. It's like you go, it hurts. I'm old. Okay, moving on. Okay, so earmuffs, and we've got to be careful, okay? Ears are delicate. You don't want to do anything to those. You need it. Okay, we've done that one. And we've done that one. Okay, oof, wow. The board's determined to go backwards. I like this question. I chose this deliberately, grade 11, because there's lots to it. And it's all about getting to the question. An automatic focus camera uses an ultrasonic wave to focus on an object. Okay, I didn't know that. The camera, ultrasonic means you can't hear it, by the way. It's very, very high-pitched. The camera sends out sound waves which are reflected off distant objects and returned to the camera. So have you ever wondered, I have a camera that does it, that automatically focuses for me. How does the camera know it's not alive? By doing this, okay? A sensor detects the time it takes for the wave to return and then determines the distance an object is from the camera. This is brilliant. So, if that was just actually putting everything in context for you, grade 11s, it's got nothing to do with the actual question in terms of working it out. If a sound wave, which has a speed of 344 meters per second, returns to the camera 0.15 seconds after leaving the camera, how far away is the object? This is what's happening. My camera is over here. The object is over here. The sound is going from the camera, coming back to the camera, in 0.15 seconds. The 0 can disappear now. They want to know how far is the object from the camera. Let's think this through. There's a couple of ways you can do this, okay? For me, the easiest way to go is, well, if the time that I'm given is the time it takes to go there and back, assuming that it takes the same amount of time to get there as it does to come back, what that means for us is if I was only considering going in one direction, it would be half the time. Okay? So the time taken to travel just to the object would be 0.15 divided by 2. Okay? Which means it's sorry, I need to get, I can't even, it's been a long week, I can't even do this one in my head. Okay, would be 0.075 seconds, okay? We know the speed, it's 344. So if V is delta X divided by delta T, we want delta X. And we get 25.8 meters. But I said to you there's another way we could do this. And I'm hoping some of you are thinking about this. Camera, object, goes there, comes back. If I work it out and I do this, if I say, well, let's do V, delta X over delta T. Velocity is 344. My distance is what I want. If I use the time 0.15 seconds, delta X becomes 57.6 meters. Okay? But that 56.7 meters is going there and coming back, so it's twice the distance. So therefore, the distance, okay, I've worked out delta X. I can't use it again as my symbol. Is actually 25.8 meters. Same thing. Doesn't matter. So you've either got to divide your time by 2 or your distance by 2, because this is the same as an echo. Sound is being reflected off an object. Okay? Ty, do you have anything else there just quickly? Because the next set of questions use a different formula, and I think I'd rather do that after the break.
Let me see. I've got a couple here. Yes, there was one question is, why can light, well, so this again with the whole vacuum.
Yeah.
More as in explaining how light then travels through a vacuum.
Okay, it's because it's the way it's made. Light is an electromagnetic wave, okay? Light is made from a moving particle. That moving particle creates a magnetic field, which in turn creates a magnetic electric field, which in turn creates a magnetic field, which in turn creates a magnetic electric field. So because I'm working with a magnetic field and electric field and not the movement of particles to transfer the energy, light can travel through a vacuum.
Yeah, okay. Then Takalani also wanted to find out what causes echolation and how does echolation affect our hearing?
Okay, I think he's talking about echolocation.
Echolocation.
Echolocation doesn't affect our hearing at all. We can't function by echolocation. Dolphins and bats do. And it's echoes. Literally what they do is they send out high frequency sounds, okay? And then they can judge, they're so clever, when the sound bounces back to them, they're able to, in their heads, which freaks me out, they can calculate straight away how far that object is, what it's made of, is it hard, is it soft, how, what distance, all of that sort of stuff. So they do it by sending out really, really high frequency sounds and judging by the echo how far away it is, basically. Yeah.
So for instance, they would shout, well, sonically they would shout and it would bounce and be like 1, 2, 3. Then when it comes back, it's like, oh, it's 3 meters away.
Yeah, pretty much. That's exactly what it is. But of course, it's instantaneous.
Yeah.
And bats have to fly with their mouths open.
That's also weird.
Yes, they have
But
to.
they catched in at the same
They
time.
They catch. No, they don't actually. It's to catch the sound. They don't have ears.
Yes. Oh, yes, they don't.
They don't actually.
Then there's another one by Nsako. Well, this is more of a statement slash reverberation. This is the process where echoes are heard from different places.
And it's when the echoes clash with each other.
other.
It starts to become a standing wave. And it's also, you get reverberation when the echo, where the object that it's echoing off isn't far enough away for you to get a clear echo. So, like, even in the studio, before they put in our stuff in the roof, I mean, you remember,
Yes.
it echoed badly. It was quite a thing.
Yes, and our sound people were like, oh,
Yeah, they didn't like us. But that's because it wasn't echoing, it was reverberating because it's not big enough to get a nice echo. School halls reverberate because it's a small, you need to be, and I don't want to lie, you got to be a good few, it's in the tens or hundreds of meters away from something before you hear a proper echo where you can actually hear the sound like properly.
and come back.
Yeah, it actually sounds like a word. It doesn't sound like a yeah.
Like that waffly kind
Yeah,
of
yeah,
underwater
where-
sound.
Yeah, where it all sort of just like gets muffled and you don't know what's going on. Yeah.
All right. So
Cool.
on that note, I think we
We
should...
can go for a break.
Yes. So mindset is, as Tracy just said, now make sure, but yeah, besides what Tracy just said, make sure you don't just disappear and just go away. Make sure if you are going anywhere, toilet, whatever, go do whatever you had to do, but make sure you come back because after the break, we've got a lot more stuff that we have to cover. So on that note, we'll see you after this break. And welcome back, Mindsetters. I hope you had a nice little break. You didn't go wander off too far away from the TV. You're back and you're ready to pay attention. You got your pens and pads out and ready to make notes. So as I said, make sure you're paying attention. And again, Mindsetters, post on the page because I'm looking for someone to give this to. So on that note, this is where I hand over to Tracy, who's going to continue the rest of the show. Tracy, take it away.
Thank you, Ty. So, last effort. I know there's some questions coming through. We are going to get to them, and we're going to get to the challenge question. But we've just used V equals delta x over delta t, but there's actually another equation we need to look at, which is what this question's about. So, it says, calculate the frequency in hertz. Okay. And important, so it's a two-part question. And wavelength of the annoying sound, no, not of a grade 11, made by a mosquito when it beats its wings at an average rate of 600 wing beats per second. Assume the speed of sound is 344 meters per second. So, first thing is frequency. You know what? They've actually given it to you in the question. I hope somebody's screaming at the TV going, I know, 600. Okay, if there's 600 beats per second, they're telling you that your frequency is 600 hertz. Remember, frequency is the number of oscillations or the number of wavelengths, the number of vibrations, the number of complete cycles, any of those per second. So if it flaps its wings 600 times per second, that's the oscillation, okay? So we've done this part of the question. Brilliant. Now we want the wavelength, and we go, well, now I need to do a calculation. Remember, you have this equation. It's the wave equation. V equals F times lambda, okay? Where V is 344. Frequency we've just worked out is 600. And we want the wavelength. And I'm hoping you guys are going to go, well, actually, you know what? It's a mosquito with really, really, really tiny wings, and they are tiny. Going to be a small wavelength. Okay, so wavelength is going to be 344 divided by 600, and we get 0.75 meters. Okay, it's a small wave, which we expect. It's a relatively high frequency. Okay, 600 beats per second. That's not small. Okay, that's annoying. That's also what makes it that horrible high-pitched sound. Okay. Yeah, pretty much. Shh. Okay. I'm just going to tell him to keep quiet because I can. So, let's do another question and then we'll get to everyone else's questions. Okay. Wrong way. Wrong way. Okay, you know what? This board doesn't like me. Okay, This board really doesn't like me. Okay, we're going to go this way. And I want that one. There we go. So, humans can detect frequencies as high as 20,000 hertz. We spoke about this earlier. Assuming the speed of sound in air is 244 meters per second, calculate the wavelength of the sound corresponding to the upper range of audible hearing. In other words, what is the wavelength that goes with a 20,000 hertz sound? That's what they're asking. So, V equals F lambda. V is 344. Frequency is 20,000. High frequency means we are going to get a very low or small wavelength, okay? So your wavelength becomes 344 divided by 20,000. Naught comma 0.172 meters. Okay? Nice and small. So, Ty, I do have some more questions, but I think there's some coming through to the page. Do you want to let me see if I can answer those?
Okay, let's tackle some of these.
Okay.
Right, so while I wait for my Facebook to load, again, I tell you mindsetters, make sure you get on the page, let us know what you're thinking, if you're lost in, if you need help, or if you just have some really cool insights you want us to know, post them up on the page. Yes, so here we are. Okay, so Michael Lisabani wanted to find out. He says, I need help. They say waves with a frequency of 2 hertz are generated in a spring. The wavelength is 0.4 meters.
Yes.
Calculate wave speed.
Okay, so let's see what he said, that waves are frequency.
Waves are waves with a frequency of 2 hertz.
Yes.
Are generated in a spring.
Okay.
The wavelength is 0.4 meters.
Mm-hmm.
Calculate the wave speed. He's stuck on how he could change the formulae.
Well, actually, this is quite an easy one, because now they want wave speed using the wave equation. You don't have to change anything, because wave speed is frequency times wavelength. So you know frequency is 2. The wavelength they said is 0.4. So that's 0.8 meters per second. You don't have to change anything. You say straight substitution.
Oh, right.
Wasn't as hard as it looked. It was just because it was different to what we were doing. Mm-hmm.
So then, Pucky, or I call him Hero, he said, what are harmonic sound? What are harmonics of sound?
Okay. Whole another ball game there altogether. Harmonics basically are when you, and we're going to just really briefly, it's an optional section, so I've got a feeling your teachers decided to teach the physics of music, which we opted out of doing because my kids were bored. How rude. Anyway, harmonics depend on whether you're playing, for example, an instrument that is closed at the end or open at the end. And remember that when a wave is created and you have a wave traveling down a flute or on a guitar or whatever, it reaches a boundary and then it gets reflected back off the boundary. When it gets reflected back, the reflected wave interferes with the first wave. And the way those waves interfere create the harmonics, okay? So that will determine whether it's and that also creates us our different notes in some ways. It gets very complicated. So you get your harmonics, and that's how we get the different scales, basically, in very, very basic terms. But it really is your harmonics come from the interference of the original wave and the reflected wave inside the instrument.
Okay. Yeah. Then, Takalani wanted to find out, can you please explain a bit about resonance?
Resonance is one of those interesting ones. Resonance is where you get a sound wave to match the wave of the molecules in a structure. Best example, I'm hoping some of you have actually seen this on TV. I've never actually personally experienced it, but I have seen it. And I know it can be done, where you see those opera singers who reach those high notes and they break glass. Okay?
Yes.
But they can only do it with crystal. It's got to be crystal glass. It's very specific. What happens is in the glass, the molecules that make up that glass, the crystal structure, all vibrate. Okay? Particles in anything vibrate all the time. When you reach the right note, that note means the sound wave you're creating is the same frequency. So the the molecules in the glass and the frequency of the sound that's coming towards them are the same. They interfere constructively, and they create what we call a standing wave. This now increases the amplitude of the wave. Doesn't change the frequency, increases the amplitude. By increasing the amplitude, we give it lots and lots of energy, and eventually they just vibrate too much that they break. Doesn't just happen with glass. It's happened in America, and I can't remember exactly where, but those big bridges, they can swing. Much to our horror. Not the little swing bridges, like, I'm talking the big metal ones, the big ones, okay? They do swing because of the vibration and what they're made out of. And there have been cases where the bridges start swinging so much because of wind and traffic and all the rest of it that it reaches the same frequency as the particles of the bridge and they collapse, okay? So resonance is when the frequency of sound that's created matches the frequency of sound of the object, and it increases the frequency, it increases the amplitude. Yeah.
Okay. So, then there's another one that came from Takalani. He wanted to find out, let me just, if I can get this wording right. He wanted to find out what will happen when two sound waves meet that are in phase but with different amplitudes.
Okay, I can do that one. So, Takalani, two waves in phase meet different amplitudes. Brilliant question. Wave 1 comes this way. Wave 2, let's do, if they're in phase, so wave 2, we're going to do it from this way. I've just got to try and draw it. So wave 2, say, is that. I think that's what he's asking. Okay, not really in phase, just pretend. That's actually terrible. Let's not pretend. There we go. That's better. Now, those are two waves that are in phase that meet each other, okay? What happens now is they still increase their amplitude, but not as much as if they were both the same amplitude, okay? So the resultant here, and I've run out of space at the top, so I'll do it here, will still be a higher wave. If they're out of phase, which is actually more, and is a more important part. So if they meet, and now we've got one wave that's like this, and it meets a second wave that's out of phase with it, but isn't quite as big, okay? Once again, ridiculous drawing, just bear with me because I can't draw. Instead of becoming 0, which is what should happen, this one actually ends up with a resultant wave that is slightly smaller than that green one. So the blue would be your resultant wave. It doesn't cancel it out completely, okay? You would get an amplitude that is pretty much the difference between the two. So it's very, very rare for waves to meet exactly in phase with exactly the same amplitude.
Okay.
Yeah.
So then another one came from Tsako, because you see, this is where I'm trying to find this very interesting, because now it's getting a lot more into the music side of things. Because then, how does a microphone produce sound?
That's, well, like the microphones we were in. The microphone has a component inside the mouth, and I won't put my hand over it, otherwise Mr. Sound Guy will kill me. Okay, sorry, Mr. Sound Guy. But the microphone picks up the vibrations. Those vibrations, there's a little part on the front end of the microphone that picks up the vibrations, that vibrates itself, converts those vibrations into an electronic signal. So you have pulses of electronic signal going down the line. If it's on, here it then goes through all sorts of things before it gets sent through to your TV. But on a stage with a singer, it will go through an amplifier, then goes through a mixer, and eventually ends up on the speakers. All of that is done electronically. And it's all electrical system signals. Once it gets to the speaker the electronic signals make the speakers vibrate. That vibration causes the air to vibrate, which is then what you hear. So it's all about converting your sound energy in the microphone to electrical energy.
Okay.
Yeah.
So then we have another one.
It has to be the last one.
Okay. This one was, okay, let me think, because there's a couple of them.
Oh boy, doing well.
Okay, one of them was that, what is timbre?
What is?
Timbre.
That's a musical term I'm not sure about.
Okay. So on that
Sorry.
note, we can go on to the challenge
Next
question.
challenge question, which we're going to have to do in 2 seconds flat. Okay, which is fine, not even because we don't have that much time. Okay, challenge question. Biggest hint. Travels faster X than Y. X travels faster than Y and has a much shorter wavelength. They are different wave motions. X travels faster, Y travels slower. So if we look at this, okay, what type of wave motions can they be? First of all, cannot be microwave and red light because they will travel at the same speed. They're both electromagnetic. Cannot be radio and infrared because they're also electromagnetic, which then means it can either be red and sound and ultraviolet, but X travels faster. X has to be the light because sound travels slower than light. So it has to be C, and I'm hoping people got that.
Yes, I'm seeing a lot of them.
Brilliant.
Get it? Seeing a lot of them.
Oh, that's bad. Ty, I think it's time to say goodbye.
Yes.
On that note.
So on that note,
Oh, my
that
word.
horrible note. Get it? Note again.
I got
Use
no.
it.
Let's just say goodbye, Ty.
Anyway, on that note, make sure, Mindsetters, you spread the word. Tell your friends to tell friends to get on the page, chat to us. And on that note, Liberty, I want to say thank you for sponsoring and take care. We'll see you next time.